Can you hear me, Sarnak?
Not clearly.
Hi, can you hear me?
Hi Anil, good morning.
Morning. Hey, can you hear me now, Suratna?
Yeah, I can.
Yeah, yes.
Okay.
Krishna?
Yeah.
Hi. Yesterday, I looked up on the Arakelov version of the Seshadri constant,
Yes.
and I found that it was used in some height function estimates and all, some Diophantine approximation and all.
Really? I see.
Was
That's very
considered,
interesting. Okay, nice to know that. So, what is the?
I can send you the article later.
Yeah, I would like to see. I mean, I may not know the full context, but it would be nice to see.
Normally, it's used for k-rational points. You want to bound it by a height function,
Hmm.
and somehow it arose naturally. Seshadri
Oh, I
constant was
see.
a crucial thing in that.
Oh, so this is. Do you remember the author's names?
I forgot.
Yeah. Anyway, we can talk later.
Yeah.
Yeah, it's now 10.
We can start.
Okay. Okay, so we can talk later. So shall I start?
Yeah.
Okay. Welcome everyone for the second day of this conference. Our first speaker today is Anilatmaja Arya Somayajula. He'll speak on sub-convexity estimates of cusp forms associated to co-compact arithmetic subgroups.
Thank you. How do I share?
You can share, I think.
Right. So you see my screen, right?
Yeah.
Yes.
Okay, so firstly, many thanks to the organizers, especially my good friend Asazad, for the invitation to talk in this nice conference. So this is this work is, I mean, most of it, or in fact, all of it, is basically in collaboration with Dr. Bhaskar Balasubramanian from ISA Tirupati, Pune. And so this is a talk which is pretty elementary in nature, I mean, I don't have as good a handwriting as Dr. Krishna, nor do I have the eloquence of the other two speakers yesterday. So it was a late night decision to take this out and make it into a Beamer presentation. So there could be quite a few typos and errors floating around, and my apologies even before we start with that. Okay, so the talk, of course, we'll see as a couple of the motivation. The motivation comes from a seminal remark or letter by Sarnak, and then something about the idea of the proof and how it can be generalized to higher dimensions. And yeah, so there we go. I'm audible, right? All is so should I be? Is it all right?
No, this is fine. Clear.
This fine.
It's clear.
Okay.
Yeah.
Okay, because sometimes my speakers have an issue. So okay, so let me just start with some preliminaries. I mean, I won't go. I mean, certain things I won't explain right away. But during the idea of the proof, again, you see, there's another chapter on background material, wherein which I'll explain them in detail. So of course, the most basic thing is the hyperbolic upper half plane. The most basic example of a negatively curved manifold, and of course complex. It's a complex. It's a Riemann surface, and one looks at a co-compact. A particular I mean, okay. It's so now gamma can be pretty much any co-compact function subgroup. By co-compact, what we mean is when you look at the action of gamma on H, the quotient is basically the quotient is a compact hyperbolic, compact Riemann surface. So by function subgroup, you mean any discrete subgroup. So any SL, I mean SL to Z, for instance, is an example. But I'm asking the co-compactness, but it need not be co-compact as long as, I mean, in fact, any function subgroup would do. When I say cofinite, I would mean basically that the quotient space has a finite hyperbolic volume. Okay, it acts by this famous fractional linear transformations, also known as Mobius transformations. Any Z or Z is sent to AZ plus B by CZ plus D. And as I said, I talked about the quotient space. The quotient space here in this particular case, I'm interested in exactly two cases. When gamma is a particular co-compact function subgroup arising from a quaternion division algebra. So geometrically, all it means is it is just a compact hyperbolic Riemann surface with arithmetic on it. All right. And the other case is gamma is SL to Z. These are the only two cases we'll be talking about, and I'll explain the structure of this particular co-compact function subgroup during the later half of the talk. For the moment, one can just think of, but for this slide, it's sufficient to think of any function subgroup essentially. And if your gamma is, say, one can think of gamma not n, and then it will be a non-compact finite volume hyperbolic Riemann surface. And so throughout the talk, I'll be identifying X with universal coverage. And the hyperbolic metric, the natural metric on X, the one-one form associated to this metric, locally at any z equal to x plus iy, it is given by the following formula, very well-known thing, I by 2 dz bar by imaginary part of z square, and it has constant negative curvature minus 1, and it is a natural metric which is compatible with the complex structure on X. The next thing is the distance function. The distance function, which is induced by this hyperbolic metric, essentially denoted by d hype. And again, I'm identifying X with H. When I write X plus Iy, I'm identifying X with its universal coverage, the local coordinates, and W be U plus Iy. Then the hyperbolic distance satisfies this famous formula, cos square of the hyperbolic distance by 2 is given by z minus w bar absolute value squared by 4 times imaginary part of z times imaginary part of p, w. I mean, this formula, in fact, like it runs, I mean, surprisingly, or maybe rather not unsurprisingly, it runs across all Siegel, all constant negative curvature minus 1 domains. I mean, basically all hyperbolic spaces, we find this formula holding true. Be the Siegel, be the complex higher dimensional spaces and all that. So this is a rather curious observation. And now let delta hype denote the hyperbolic Laplacian acting on smooth functions in X. That is at any point, again, identifying X with H, it is given by the following formula. It is just the Euclidean Laplacian times minus y square. That's all. All right. It is a natural Laplacian compatible with the complex structure on X or compatible with the metric. It depends on which way you would like to look at it. I mean, so these are all the basic things required. And so the important part is Sarnak's conjecture is something on eigenfunctions of the Laplacian. Hence, I have to come up with all these definitions. Sarnak's conjecture tells us, I mean, basically speaks about the growth of eigenfunctions of a Laplacian, which will very soon. Yeah.
Sorry to disturb. There was someone raised a hand. Do you want to?
Yeah. Yes, please. Yes.
Yeah. Go ahead. Whoever raised a hand, can you ask your question? Okay.
Are they typing? I cannot see if they're typing.
No, they're not typing. Okay. So anyway,
unmute. Can you please?
Yeah. Can you unmute? I see. Someone has to unmute there. Okay.
Yeah. So I'm requesting the host to unmute, please. Hello. Hello, Manish.
Yeah.
Yes, sir.
So one person in attendees is raising. Yeah, go ahead.
Yeah, I have just a very simple question. Any particular advantage for using hyperbolic Laplacian as compared to classical Laplacian?
I mean, I said this is a natural Laplacian compatible with the complex structure on X. So we're looking at things which are defined on X. So Euclidean Laplacian will not be an automorphic. So for instance, your your Riemann surface is gamma invariant. I take a point Z and any gamma Z are equivalent. The Euclidean Laplacian is not invariant under the action of gamma, whereas this guy is invariant under the action of gamma.
Thank you.
I hope that answers.
Yeah, it does. It does. Thank you. I'll mute myself.
Okay. So now, yeah, that was a good question. Maybe I should have. So I missed the. Okay, now coming to the main players, these eigenfunctions. Since X is compact, it's well known the spectrum of the hyperbolic Laplacian. The eigenvalues of the hyperbolic Laplacian are all discrete. So we gave a numbering 0, lambda 1. Lambda 1 is the first non-zero eigenvalue, and then the others can be equal. I mean, there are several conjectures on the lower bounds of lambda 1 and all that, and these are all very difficult questions which go into spectral theory and all that. So most of them are unanswered still. Now let phi n denote, we can choose these eigenvalues to be real valued. I mean, that follows from simple elliptic. Because it's an elliptic operator, certain basic regularity theorems ensure you can get a real valued function, normalized and orthonormal. So let this phi n be a set of real valued, normalized, orthonormal functions corresponding to the set of eigenvalues lambda n. So what do I mean by that? I basically mean that each phi n has eigenvalue lambda n, and when I integrate phi n with phi m, it's equal to 1 if m is equal to 1. That is phi n square mu height z is 1, and phi n phi m when integrated when m is not equal, then it is 0. So this is a set of orthonormal eigenfunctions. I call them normalized when integration of phi n square over mu height with respect to mu height over x is 1. Okay. So these are, in fact, these are called Mäss forms, named after the famous German number theorist, geometer Mäss. And so now let phi be a Mäss form with corresponding eigenvalue lambda. Then from basic techniques from differential geometry, inner product inequalities and all, it is easy to prove that the maximum value, I mean, supremum over z belongs to x for phi of z in terms of lambda. It can be bounded by a constant which only depends on x, the Riemann surface, or equivalently gamma, because gamma determines x and x determines gamma by the Riemann uniformization theorem. So it is the growth of phi with respect to lambda is lambda 1 power 4, and this is called the convexity estimate. And one cannot expect any better. This is all that one can expect, and this is what it will be. However, if you're lucky enough, that is, if you're working with space which has some arithmetic on it, then you have this concept of Hecke operators. And if you have Hecke operators coming in, it is an algebraic theory. And if so, in a way, if you can say that if your phi is somewhat algebraic, then you can lower it much more. And that's where Sarnak's conjecture is based upon. So let me define what a Hecke operator is. So as I said, I'll be a little. So you cannot define it. Hecke operators, as I said, are algebraic. They cannot be defined for any Riemann surface, but you can only define them for Riemann surfaces which are arithmetic in nature, or rather the gamma is arising. Gamma is actually arithmetic. That is to say, gamma is a co-compact Fuchsian subgroup which arises from a quaternion division algebra. I'll describe the structure later on. For the moment being, we can just assume it has some arithmetic on it, and it arises from a quaternion division algebra. All right. And then for any n belongs to any positive integers, the Hecke operator acting on L2x is given by the following action. It is just this. So here, of course, your gamma, which is basically an arithmetic subgroup, each element of gamma acts on gamma n. I mean, if you look at this, gamma n is essentially all this. There again, the set of certain 2 cross 2 matrices of determinant n. And each gamma is, of course, is all said and done, it's still a subset of SL2R. So each element of gamma acts on gamma n by left multiplication. So you can look at the cosets, and you can take any coset representatives and some f over gamma z's. All these Hecke orbits are called. If you can sum over them, that's the Hecke operator. So Tn of f is basically summation of f over these Hecke orbits. And L2x, of course, as you see, denotes a space of square integrable functions on x. And as I said, gamma n, I'll describe gamma n later on, I mean, if you want to be more precise. But for the moment being, it suffices, as I said, it comes from an arithmetic, so it has arithmetic on it. Hence, you can talk of such a gamma n, and then you look at these cosets, left cosets, because of the action of gamma on gamma n by left multiplication. All this is well defined. So once you have a Hecke operator, there's a lot of algebraic theory behind this. Then a mass form is called a Hecke eigenmass form if Tn of phi is basically just lambda phi n. This lambda phi n is called the Hecke eigenvalue. It's I mean, it's a complex number. Well, more traditional number theorists would basically massacre me if they find that it as complex, because in fact, a lot of, again, this is a big area, big industry, the algebraicity and then the irrationality. I mean, of course, for sure, this is a real number. More of a, I mean, so there are several conjectures on these Hecke eigenvalues, if they're algebraic, and like how many of them are zero and all. There's a big industry in analytic number theory. All right. So, but given
your gamma
yes.
is a Fuchsian group, right?
Yeah, but it's a certain arithmetic Fuchsian subgroup. It's not any. That's what I was saying.
Yeah, certain arithmetic, but for gamma n, you are saying matrices of determinant n.
Yes. I mean, so there's a way to, for instance, if your gamma is SL to Z, then gamma n is just all determinant n matrices. I mean, 2 cross 2 matrices with determinant n. That's all.
Okay.
But that is not co-compact, but this is co-compact. So this is arising from a, so there is a certain division algebra arithmetic behind it. I'll come to it in the later part of it. So for the moment being, it suffices to know that there exists an algebraic operator with certain algebraic properties. And that's how it's defined to be. Are we good?
Okay, go on.
Okay, so like I said, this lambda. So now, I mean, in fact, so the point is, like, you can, in fact, so it's though it looks like a difficult and stringent condition to attain, you can in fact find an entire set of eigenfunctions for the corresponding spectrum of the Laplacians. I said all of them are Hecke eigenmass forms for each n belongs to z greater than 0. So you can cover your entire spectrum by Hecke eigenmass forms, normalized, of course, and this is quite a strong thing. So they are quite relevant in nature. Now the sub-convexity estimates, that is, if you want to go below lambda power 1/4, it is possible only when your mass forms are Hecke eigenmass forms. So this is where the seminal paper of Ivanich and Sarnak comes in. It was a paper in 1995 in Annals of Mathematics. So they proved the following estimates. Again, it's the same gamma, which is coming from a quaternion division algebra, and whose structure I'll describe in the next slides. And let phi be a Hecke eigenmass form on X with eigenvalue lambda. Then for any epsilon greater than 0, we have the following estimate. That is the supremum of the absolute value over a Z ranges over X is just dependent on gamma and on choice of epsilon, and the growth with respect to lambda is 5/24. it is in fact less than 1 by 6. So it was quite a thing to come from 1 by 4 to less than 1 by 6. And so this is this involves. So I'm not really an analytic number theorist, but from what I understand, perhaps is maybe there's a technique called amplification. It arose. I mean, it arose from these estimates and all, which is again quite prevalent in analytic number theory these days. So, and of course, in the same paper and in appendix, they could extend the methods when gamma is SL to Z. They are the same estimate essentially. Until date, these are still the best estimates possible. And one might wonder what are these estimates, how are these estimates, or even, I mean, I wrote O epsilon without gamma here because SL to Z is basically O of 1. So I took off gamma there. Of course, here it depends on the quaternion algebra. Actually, if I, okay, it depends on the quaternion algebra or gamma essentially. And so why are these useful? And like, I mean, as far as I understand the way, so there are 3 difficult problems. Number 1 is, of course, your Ramanujan conjecture, that is Fourier coefficients of mass forms or automorphic forms. The second one is their estimates. And the third one is the quantum unique ergodicity. That is the dynamical, that's a problem in dynamical systems. That is, so as your lambda goes to infinity, how will how will a measure arising from phi behave? It should behave as exactly like mu hype is what the conjecture says. So of them, I mean, this quantum unique ergodicity is proved for a lot of cases. And this guy, so the major technique has always been the Fourier coefficients, estimates of the lean, and of course estimates of these automorphic forms. So estimates of automorphic forms are very essential for ergodic theoretic or a dynamical system theoretic point of view. So they're very useful in proving these kind of quantum quantum ergodicity conjecture theorems and all that. Okay, so I mean that's one thing I know of. And so maybe yeah. So now this is in the C infinity world. Your phi is basically a C infinity function. Now, of course, I mean, so of course one would like to see what happens in the holomorphic case. Okay, so this is what Sarnak and Riemann proved. And after he proved, he wrote a famous letter to PD person, Kathleen Moravec, famous professor in partial differential equation. So, and he made the following conjectures. I mean, not in the exact form. I mean, over a period of time, he refined them. So when gamma is coming from a quaternion division algebra and gamma is co-compact, then he expects it to grow like lambda power epsilon. This is rather strong, and we are far away from that. And when gamma is SL to Z, expects 1 by 8 epsilon, 1 by 8, lambda power 1 by 8. And both are very far away. We are still very far away in the sense like the estimate proven by Sarnak in 95 is still the best known estimate in both the cases. It's still the one to beat in the C infinity world or the mass form world. And in automorphic forms, you have the corresponding thing, the holomorphic world of cusp forms. Or the modular forms, as I mean, some of modular forms have become very central to mathematics in recent years. And like long back, Martin Eichler remarked that modular forms are the 5th fundamental operation. And by that, he meant that they were quintessential. That's what he meant. And yeah, so one would like to see these conjectures in the context of modular forms. And I'll give you a heuristic reasoning why cusp forms are analogous to cusp forms or modular forms are analogous to our to these mass forms. So let me define what a mass form is, sorry, cusp form is. So it's again, let gamma be any co-compact function subgroup or SL to Z. Okay, for the moment being, let it be a co-compact function subgroup. And for any positive integer, it's a function, it's a holomorphic function going from H to C. It's called a cusp form of weight K if it satisfies, firstly, should be holomorphic on H. And for any gamma belongs to gamma and any Z belongs to H, it satisfies this famous transformation formula f of gamma Z. Gamma Z is, of course, AZ plus G by CZ plus D. That's equal to CZ plus D power K and f of C. This is the famous transformation formula. Then it's called a cusp form. In fact, for a co-compact function subgroup, it wouldn't have any cusps, or the corresponding geometric structure Riemann surface will not have any singularity, so to say. So it is a compact smooth guy. So there are modular forms and cusp forms are the same. But however, if you have SL to Z, then if it only satisfies, you should satisfy the extra condition that it should vanish at, it should be holomorphic at I infinity, which I forgot to mention, and it vanishes at cusp of gamma. I think this is fine, I guess. Vanish at the cusp of gamma. I mean, gamma when SL to Z has only one cusp, which is I infinity, and at that point F should vanish. Then it's called a cusp form. As I said, I restrict myself to these co-compact function subgroups and SL to Z, because other arithmetic subgroups or finite index subgroups are finite index subgroups of SL to Z, and the theory is pretty much the same. For brevity of exposition, I restrict myself to just SL to Z. And SK gamma denote the space of weight K cusp forms, and it easily checked that they form a complex vector space. All right, and so far, so these are the cusp forms. I'm sure most of you know it. And then they have this Petersson inner product for any FG belongs to SK gamma. I mean, one should remember that F and G are functions on H, but however, this particular guy, F times G bar times Y power K. By this, I mean, I'm taking Z to be X plus IY, again, identifying X with H. I really should be writing a fundamental domain. We fix the fundamental domain, but I've been a bit, yeah, I've not been so careful, so to say. So let these are the Petersson inner product is defined. It is Y power K times F times G bar. This is automorphic, that is, it is a function on X. That is, it's invariant with respect to action of gamma. So these are the Petersson inner product is defined. And by that time I am identifying X with H. It's given by the following formula. It's Y power K by 2 absolute value of F of C. So that's how it's defined to be, and one can quickly see if one knows that the imaginary part of any gamma Z is just Y power CZ plus D whole squared. One can quickly compute that this is actually invariant with respect to action of gamma, for the same reason as the inner product is invariant with respect to action of gamma. So this in fact defines a function on X. So it makes sense to talk about this guy as a function on X. Now, this curious observation, which begins with this weight K Laplacian. You have this thing called the weight K Laplacian, which is not a homogeneous operator, I mean, non-linear. It is a minus y square, the usual. Okay, yeah, the y square missing. Yeah, the typo was which crept in. Minus y square, but it's a standard Euclidean Laplacian times minus y square plus I times k by dou x. Yeah, so this is, I mean, each of these have their own significance and their place in number theory. But for the purpose of this talk, I just stop and just say that this is basically, I mean, just another differential operator. And one can look at the crucial observations as follows. You take any cusp form of weight K, and at any Z belongs to H. One can see that Y power K by 2 into F of Z, not the absolute value. It's just Y power K by 2, just this guy, without the absolute value. This guy is actually an eigenfunction for this Laplacian, and with eigenvalues K by 2 into 1 minus K by 2. So the eigenvalues are actually negative in nature, but nonetheless, the important point is that, I mean, you can change that by changing the sign of the Laplacian and all that. But as I said, the important point is this is actually, it is an eigenfunction for a, I mean, it is associated with an eigenfunction of a Laplacian essentially. All right. Now, so yeah, so it's like an it's an eigenfunction for a, it's related to an directly related to a eigenfunction of the hyperbolic Laplacian, weight K Laplacian with eigenvalues. Now, when simple theorems in dynamical systems would tell you that, I mean, mass forms are eigenfunctions of delta hype, and whatever kind of estimates they satisfy, even this guy should also satisfy similar type of estimates. That comes from Hartmann, Grobman, and all these basic theorems from dynamical systems ensure that you can go from linear. I mean, so you can go from, yeah, so this homogeneous thing to a linear thing to a non-linear thing. Okay, this is not linear, but yeah, so you can go from the hyperbolic Laplacian to this guy, though you have this extra non-linear term. You can still there exists some kind of an isometry which preserves things, so one can expect similar kind of estimates. Only difference is, so now we can think of F as an eigenfunction of a Laplacian with eigenvalue k square, not In the case of mass forms, it's lambda. Here it is k square. So if you just make the keep that in mind, one can make sense of Sarnak's conjecture and all in this case as well. So again, by going by the theory of dynamical systems, one expects the following convexity estimate. I mean, I said k1 by 4 was lambda 1 by 4 was the estimate there. Since here it is k square is the corresponding eigenvalue, the Petersson norm satisfies of root k. So it's exactly the same. And this, if you know some basic theorems from complex geometry, and also if one knows that one can identify the weight k cusp forms as sections of the, I mean, in fact, the space is isometric to the cotangent bundle, tensored k by 2 times. And of course, here you have the Petersson norm on the left-hand side. On the right-hand side, you have this usual norm coming from the hyperbolic metric. And if one knows that these two are isometric, then complex geometry will tell you how these sections would grow. That's a standard. That's a very. I think it goes back to Tian and all. A lot of work has been done. Tian, Demeli and all. It's very by now it's very trivial. I mean, it has become yeah. So this is very easy to prove that not easy to prove, but it's well known that they satisfy this. So sections of the cotangent bundle satisfy exactly this estimate. And I'm sorry, sections exactly satisfy this estimate, and hence so this estimate is which is exactly what sections of, I mean, elements of SK gamma should satisfy. So this convexity estimate is trivially achieved, so to say, and one cannot expect any better unless you have something more. Of course, the Hecke structure, which first came for actually cusp forms and then was taken to the L2 case, to my understanding. So Hecke operators and SK gamma. So again, as said before, we only consider co-compact arithmetic subgroup arising from a quaternion division algebra, or when you look strict to S gamma equal to SL to Z. Now, as I said before, what Suratna asked, gamma n denotes the set of
Anil,
matrices.
can you go to the previous slide? Was there a typo? I was just wanted to ensure this. So this is k by 2, or like you want to take
K by
square?
2. It is k by no. It is k by 2. That is correct.
Okay.
Where 2 cusp forms correspond to omega 1x. So differential forms of degree 1, they correspond to. Yeah, that's correct. Yeah. And this, I mean, if you have, I mean, in general, if you look for holomorphic sections of a line bundle on a compact manifold of dimension n, the sections grow exactly like O of, I mean, there is no square here. Okay. If you have the square, they'll grow like O of k power n. In this case, n is 1, Riemann surface. And I don't have a square here, so this will become root k. That's all.
So, so to be sure, so what does this notation means? Means omega 1x. This
Yeah, omega 1x basically is a cotangent bundle.
cotangent bundle. This
yeah,
tensor k by 2.
Tensored. Yeah, you look at the k by 2 differentials, that will be your SK gamma.
Okay. Not
yeah. I mean, it's not necessary that it exists. I mean, if that doesn't exist, SK gamma would not exist. Yeah, I mean, for odd k, it's not clear. Okay, so we now only consider the case when gamma, as I said, we only consider when gamma is a co-compact arithmetic subgroup, or SL to Z. When gamma is actually only this co-compact subgroup, then gamma and denotes certain set of matrices of determinant 10, 2 cross 2 matrices, and gamma is SL to Z, exactly all 2 cross 2 matrices of determinant 10 with integer entries. So, all right. Then the Hecke action on SK gamma is given by the following thing. T cusp SK gamma goes to, yeah, you have this n power k by 2 minus 1. Again, the summation over the Hecke orbits. Just this automorphic factor comes. CZ plus T power k. And these gamma acts on gamma n by left multiplication. You look at coset representators. That's exactly what it is. In fact, one knows how many elements this cosets have. How many coset representatives exist. That's a very important thing to know in the estimates. So it's exactly of n epsilon. Okay, these are the cuspidal Hecke operators defined. All right. And now any f belongs to SK gamma is called a Hecke eigen cusp form if it satisfies Again, for all Tn of f is basically some complex number times. Again, I forgot an f there, so I forgot an f here. So, lambda nf. So there should be an f here, and lambda nf is called the nth Hecke eigenvalue of f. So yeah, so then it's called the Hecke eigencusp form. And furthermore, we call it normalized with respect to the Petersson inner product if this this Petersson norm square is when integrated against the hyperbolic metric is 1. All right. So we're interested in normalized Hecke eigencusp forms and their estimates. They allow sub-convexity estimates. You can go below root k if in this particular case. All right. So now the sub-convexity estimates. Again, as I said, so now I'll let f be a Hecke eigencusp form, which is normalized with respect to the Petersson inner product. And then you have the following estimates. This is, I mean, after Sarnak and Ivanich worked on them, almost after 20 years, when Soumya Das and Jyoti Sengupta proved this following estimate, when gamma is the co-compact arithmetic subgroup arising from a quaternion division algebra as before, that is the same arithmetic subgroup considered by Ivanich and Sarnak. For any epsilon greater than 0, we have the following estimate. That is, yeah, it is 1/2. In fact, so there was a published version. There's a small error, and there was a communication between me and Soumya for some time, and eventually this is which is the corrected version which appears on his homepage. I mean, root k was your estimate. I mean, convexity. Sub-convexity is going by -1/2 by 1/31. So it's it's a very minute thing, but nonetheless, it's a significant thing, which tells you that in fact sub-convexity estimates exist. In fact, that was the main motive, to show that sub-convexity estimates exist, not that they were not after k epsilon. Okay. And one would like to know what is the similar thing in the setting of SL to Z. SL to Z would be surprised, it's rather neat. It's k1/4 plus epsilon. Zia proved it way back in 2007, even before Das and Sengupta attempted the thing. And so this, of course, k1/4. And if you remember Sarnak's conjecture, which says lambda 1/8, so k is exactly root k is your so corresponding thing. So I mean, k square is your eigenvalue for f. So that should be exactly it's a right estimate, so to say. I mean, k1/4 plus epsilon going in by Sarnak's thing. Even otherwise, Zia proved that this is in fact optimal. He proved it's optimal, and even by Sarnak's thing, it's optimal. So SL to Z was no issue at all. So it was a very simple paper, basic complex analysis, and some, of course, one cannot do without Deline's estimate, and then he had it. So why is it so easy? Basically, why is it so easy in the okay, so yeah, so Sarnak's estimates when looking at the just generalization to holomorphic version, one would expect k epsilon for the compact version, and SL to Z, or in fact any arithmetic subgroup, one would expect, which has cusps, one would expect k1/4 plus epsilon, and that's exactly what Zia proved. So you see that Zia's estimates are optimal and without much of a fuss, whereas the other ones, one is really striving hard. And the major difference is, yeah, said like Zia's estimates are optimal, and
Someone
they have
raised hand.
There is a question.
Sorry, yeah.
Someone raised a hand, so can you unmute and ask?
Sorry, it was by mistake. Okay.
Okay, yeah, no problem. Go ahead.
Okay, so yes, Zia's thing are optimal, without much fuss, but nonetheless, these have been they could be extended to all arithmetic cofinite subgroups. That is basically all I mean all finite index subgroups of SL to Z, which are arithmetic. And however, they're not yet derived for certain arithmetic subgroups. Okay, this I'm not sure, Mr. Rodin's. But however, it's clear when k is half integral, we are far from the optimal estimate. That is because of when k is half integral, the Ramanujan conjecture on Fourier, I mean, the major cog in the wheel, or the major technique used, is essentially the fact that your this Fourier, cusp forms admit a Fourier expansion, and gamma is non-compact. And as cusp for the Fourier expansion. For Fourier expansions, of course, determine the modular form or the cusp form. And one has this famous Ramanujan conjecture, which says the Fourier coefficients grow like n power k minus 1 by 2 plus epsilon, which is true. Famous result of Deligne proved way back in 74 for all arithmetic subgroups. But however, it's not yet true for k half integral. The best known estimate is still far away from k minus 1 by 2. So that again that goes back to Ivanich. Yeah, so which is why this which is why wherever the lean estimate is not known, that's where this optimal estimates are stalled. So I said that's a much more basic and fundamental problem for estimates of Fourier coefficients. And so now what is so now there's another conjecture going on in this area, goes back to Blomer and Holowinsky, same school of Sarnak. Holowinsky is a student of Sarnak, and they made the following estimate: when gamma is basically a finite index subgroup, it's a subgroup of level n in SL to Z, normalized Hecke eigen cusp form, then one expects an estimate like k1 by 4 plus epsilon, and as the level increases, then this basically goes to 0, n minus 1/2 plus epsilon. So certain, I mean, this all conjecture is also not achieved, but Saha saw some papers where he got n minus half. So I think there has been some progress on the level aspect. There's been a progress both on the co-compact side and the compact side, and the cofinite side very rapidly. But like k half integral and the co-compact side, the actual k epsilon, they're far from true. I mean, in fact, only one result exists in the co-compact side, which is basically by Das and Sengupta. So finally, coming to my recent work with Bhaskar, it is recently submitted. So here, of course, I mentioned gamma comes from a quaternion division algebra A, and as for Hecke eigen cusp form, normalized and the usual jazz. Then for any epsilon greater than 0, we have the following estimate. So we could extend it to we could bring it down by 2 from 1 by 100, roughly 2 by 100 to 1 by 12. That is, if you look at it here, it's, I mean, if a little bit of, so it's easy to see, it's just k5 by 6, no, k5 by 12, that's all it is. And if I kind of, so instead of gamma, I wrote A because after all, the gamma itself depends on the quaternion algebra A, so I just wrote A here. And it's 5 by 12. But if you go back to Sarnak's estimate, Sarnak conjectures, so Sarnak's estimate is also k lambda power 5 by 24. So going from this root k to lambda, one looks, so the corresponding here should be exactly k power 5 by 12. So that's exactly what we achieved following Sarnak's method. So Das and Sengupta adopted and adapted the method of Sarnak and Ivanich. We slightly tweaked it, and we could prove the same estimate as Sarnak and Ivanich could get in the holomorphic case. So my feeling is that I don't think you can better this estimate using those methods. I think one has to get a better saving, one has to do something, I guess, completely different and something very original. Okay, now I'll try to get to the idea of the proof, and I mean, the proof is not much. It's coming, as said, it is pretty much borrowed from Sarnak and Ivanich. Again, the key players. I was talking about this gamma SL to Z. It admits a Fourier expansion. Hence, of course, and you have the Ramanujan conjecture for k integral, half integral. As I said, there is no such thing. Hence, half integral is also open. So now gammas, I mean, Raphael Steiner, one of the persons I know, is working on this half integral. He has proved certain things, and but is still away from optimality by a big margin. Even k5 by 24 is not included. 5 by 12 is also not close to it. Now, when gamma is a co-compact arithmetic subgroup, to compensate, well, the reason why they looked at this arithmetic subgroup is you have this famous. So you have of course, you don't have Fourier expansion, but then they applied the following methodologies. So first, they took this is one of the things of Ivanich. He is a master of taking right automorphic kernels for the right things, and then this famous amplification technique, and then they invoke the famous Jacquet-Langlands, and combining these three, they could arrive at what they could arrive at. And as I said, Das and Sengupta followed that, and we also did exactly the same thing, excepting that we replaced step 1. Instead of this automorphic kernel, we took this Bergman kernel. And so Bergman kernel is something which is coming from the heat kernel, and something what I'm really interested in. So it goes back to the Bergman kernel. Now, let me define this co-compact arithmetic subgroup I've been talking about. You take an A, B, and Z, E, and then you look at the quaternion division algebra defined over Q with these two elements. You have the usual norm operator, which you may explore at infinity. That is to say, you have this embedding from A into this 2 cross 2 matrices entries coming from Q root A. And let R be a maximal order in A, and look at R1, which is basically all elements with norm alpha is 1. Now, via this embedding phi A, we can embed R1 into SL2R. You get 2 cross 2 matrices of determinant 1, and it will be discrete, and it will be co-compact because of a choice. And it is, of course, arithmetic because all the arithmeticity goes back to AB. And now the Rn is basically, you look at Rn, which is all norm n elements, and then you look at its image under phi A in Q root A. That will be a gamma n. And it is well known that gamma acts on gamma n by left multiplication. And for any epsilon greater than 0, the cardinality of the set is that is a coset of cosets exactly has growth O and epsilon. It's exactly log n, I think, if I'm not mistaken. That it grows like log n. And then the analytic world, they represent it by O epsilon and epsilon. They substitute log n by n epsilon. And yeah, so implied constant depends on choice of epsilon greater than 0. Okay, and the Bergman kernel. Now let dk be the, when as I said, Sk gamma is finite. It's a complex vector space, finite dimensional, follows from Riemann rock, and also from the isometry with the cotangent bundle tensor powers. And dk be its f1 to fdk be its orthonormal basis with respect to the Petersson inner product. And then again, one can choose, like in the case of mass forms, we can choose all the orthonormal bases to be Hecke cusp forms. Okay, so now the Bergman kernel associated to Sk gamma is given by the following formula. It is Fg, it is holomorphic in the variable Z, anti-holomorphic in the variable W. And of course, it seemingly depends, it seems to depend on the choice of the orthonormal basis, but the reality is it doesn't, because of the following a simple reason, that it's a generating function for the vector space Sk gamma. That is, you take any f and then you integrate against the Bergman kernel. Here I'm taking W to be U plus IV, and then you integrate it, and then you get it back Fc. So it's a generating function. So Riesz representation theory from function analysis tells you that it is independent of the choice of orthonormal basis. Okay. Then the pointwise norm of this is, again, because it's a cusp form in one variable, anti-holomorphic cusp form in another variable, the Petersson norm is well defined, and this defines a function on x cross x. It is independent of the choice you make for Z and W. And the important crucial aspect is it can be represented by this following infinite series, which goes like this. The important thing to remember here is just k here upstairs, they're all constants, and this automorphic factor and Z minus gamma W bar. All right. So this is about the Bergman kernel. And then the estimates of the Bergman kernel. So then one can take absolute values and see that there's actually less than or equal to this. This comes back from the Koch formula I talked about in the very beginning. So essentially it grows like of k by Koch k dHc gamma W by 2. So I was after this for various reasons. I mean, from completely different context, we could derive the following estimate. This guy is actually bounded by just Koch k dHc gamma W by 2, and only depends only on Z and W, nothing else. And the choice, the implied constant depends only on gamma. It depends on the length of the shortest geodesic gamma. That's all it depends on, nothing else. K, of course, says. So these estimates were useful. These are the new things which we brought into the proof. And yeah, the famous Jacquet-Langlands correspondence says the following thing. If your f is basically a Hecke cusp form with set of eigenvalue is this, which gamma is co-compact arithmetic, then there exists a D0, which depends essentially on the order R, maximal order R, which is again in A. There exists integers Q and D such that for all n which are prime to Q, there exists a cusp form F whose Hecke eigenvalues coincide with that of F. So given small f in Sk gamma, you can find a big F in gamma naught D. Gamma naught D, Dahleen's estimates are true. So Hecke eigenvalues, they satisfy Dahleen's estimate. So these lambda and Fs also satisfy Dahleen's estimate. So this was a crucial thing. This was one of the main things of Ivan Sarnak. As I said, from the lean celebrated estimate, you have this. And yeah, as I said, so basically it's just n power k minus 1 by 2 plus epsilon. And this is the Jacquet-Langlands correspondence. And now the amplification technique. So now we make this normalization, eta f g of n, you divide it by n power k minus 1 by 2. And then you look at this constants alpha 1 to alpha n, where alpha n equal to 0, q divides n. Q is a prime which depends only on your maximal order R of A. Now, yeah, so this is the technique. I mean, this is very common. I mean, I'm still new to it. It's quite, it's basically bread and butter for analytic number theorists. You multiply this summation by this guy, it eventually comes out to be this. There is basically the cuspidal, what's it called? The Hecke operator acting on the Bergman kernel, alpha and alpha m bar. I mean, just some values. And yeah, so here, of course, I mean, the Hecke operator acting on the second variable. And once you have this, you plug in values. Yeah, so you essentially put, so this is the eventual thing one arrives at. There's less than or equal to this. And then for this guy, we could, we put our estimate of the Bergman kernel and then use a certain counting function. And yeah, and then we have to choose for alpha and then alpha m. We choose to be again eta f p and e minus 1. A lot of Hecke arithmetic goes in here. And after applying Hecke relations, we arrive at this nasty little thing. And yes, you have to, there's the eventual thing. And you put k equal to 12 n cube log n, and then you're through. So you get n power, you get k power 5 by 12 minus 5 by 12 plus epsilon. So proof again, it depends solely on the amplification technique and the estimates of Bergman kernel. And the crucial, of course, the main thing, the central thing which allows all of this is basically the famous Jacquet-Langlands. So this is the, I mean, I was very quick because it's pretty, I mean, the computations are not so, I mean, they're not that cool, so to say. The idea is cool. I mean, just I'll take a couple of, can I take 5 more minutes?
Yeah, sure.
Okay, I mean, I just 3 more things. May not even take 5 minutes. So the reason why this is interesting is the moment you have estimates of the Bergman kernel, you can estimate the individual automorphic form. And so the next immediate thing one would look at Hilbert modular varieties. So this is a place where we already had some estimates of the Bergman kernel. So Hilbert modular group of type 1 is basically, it's a subgroup of SL2R multiplied by n times, and it acts on H, n copies of H. It is not a hyperbolic space. And it is, I mean, if it's of type 1, if it's a discrete subgroup, co-compact, that is the gamma acting on Hn is compact. And it's of type 2 if it's of a subgroup of SL2, okay, where K is any totally real field of degree n, and OK is ring of integers. It's a Hilbert modular group of type 2. These are 2 types that we considered. And you again, now K underline is basically vector K1 to Kn. So you can have, so we are considering cusp forms of not parallel weights. Parallel weights are when K1 equal to K2 equal to Kn. Here we're considering non-parallel weights. And then let F1 to Fdk. Again, as in the case of one-dimensional case, we have the Petersson norm, Petersson inner product, everything which happens in SK gamma. And of course, you have cusp forms of factor of octomorphies as expected and all that. And so the Bergman kernel again can be given by exactly the same thing, Fjz, Fjw bar. So dk is the dimension of SK gamma. Here again, it corresponds again to these differential forms. And this is an old result of ours that wherein which if it's a type 1, we proved the supremum, said the Bergman kernel Petersson norm is given by product of the y's power kj's and the absolute value of the Bergman kernel. It's exactly product of k's. If your k's are all equal, it's k power n, and that is in sync with all complex geometry estimates or predictions. And of type 2, again, our estimates are explicit. And type 2, the number theoretic case, it's K3 by 2. So this is a curious observation which he made. And this seems to hold true in a variety of places. Recently, there's a big breakthrough in the Siegel case. Professor Jörg Kramer and Antarit Mandal, they claim to have, it's still under revision and all, but there's significant hope there that they could prove, and they found a similar K3 by 2. And I mean, I was examining certain estimates in the complex geometry case, and then like the one has a famous, the famous technique where you estimate where balls of radius 1 over root k and all, and the limb slope is always of k for non-compact manifolds. The root k comes up. I could see a root k coming up in the non-compact thing, but it was not heuristically speaking. It's not written up or anything. So even from complex geometry, it's not. I mean, if it's k3 by 2 is expected, so to say. So, and the next thing is proper hyperbolic spaces, the Picard group. And now from totally real to you go to totally complex. K is now a totally imaginary field, sorry, totally real to totally imaginary. So SUN1, this symplectic group, this group acting on the ball quotients. Bn is basically Bn is basically this ball quotient. Unit complex unit ball endowed with the hyperbolic metric or the so-called Bergman metric. And then you look at Sk gamma, the complex vector space of K-cusp forms. And again, if it's of type 1, if it just is in SUN1C, it's co-compact. It's type 2 if it is a finite index subgroup, which is number theoretic, subgroup of SUN1, okay. And the Bergman kernel again is given by the same formula. And then this is what we proved. That in the co-compact case, we could prove that it's basically okay. And again, this is pretty much complex geometry, is in sync with complex geometry. But non-compact, we couldn't prove it back then. We gave it up. But then now we know what is expected. Okay, this should be n here, 3n by 2. And now a PhD student of mine is working on that, Mr. Thiroy. And yes, maybe let me say something about Siegel case. Siegel case, as I said, at least in the SP4 case, you know, Jacquet-Langlands exists. And one knows, I mean, one cannot do whatever Sarnak and Ivani achieved. One has to go to some estimates of Hecke operators coming from Ulmo and Lomo and all. And this is currently a student of mine is working on this. And because we have the Bergman kernel estimates coming from Kramer and Antari. And lastly, so of course, you have all these different types of automorphic forms, which are still sections of the Hodge bundle. One can look at modular space of compact hyperbolic Riemann surfaces of genus G. Then you look at sections of tensor powers. They're called Mumford forms. And more recently, they're being addressed as Fleischmuller modular forms. Their estimates are also somewhat interesting, but there is no Hecke theory there, but still they're quite interesting. And a student of mine is working on these estimates of Mumford forms. And like these have a resonance, these estimates here would resonate here in the cusp form setting because of the Torelli map, which embeds Mg into Ag. So there is some string linked to string theory as well out there. So I'll stop here. Thank you for your attention.
Thank you. Are there any questions?
Yeah, I have one question.
Yeah, go ahead.
Yeah, what are the difficulties of studying the same problem for non-co-compact case?
I mean, non-compact is easy. Or to say the arithmetic ones are easy because you have the Fourier expansions, but again there you're limited as you can go only as far as the linear estimates allow you to go. So Siegel modular cusp forms, any estimate is a big deal. I mean, Blomer recently had a big result, but I think Antari result is perhaps on par or perhaps even better. So it's on par with the in sync with the Sarnak's conjecture and everything. Sarnak's conjecture, of course, has a rank of the symmetric space as well, which didn't specify. It's dimension of the space minus rank by 4. I think he has that covered. So
Okay.
So the difficulty, as I said, is the Fourier expansion. You don't have Fourier expansion, you're pretty much, you only techniques you might have are PD oriented or some complex analysis. So they would have been already worked out by Tian long back, or if the Tian hasn't worked out, then they should be very hard.
So compactification will play any role here if you and
algebraically it does, right? But then analytically there is no use.
okay.
Analytic structure still remains the same.
Okay.
Any other questions? Okay, if not, let's thank Anil again for a very nice talk. Thank you. So we'll meet in 15 minutes around 10 past 11.
Hi, Sajad. I want to check my technology. Is it possible? I want to share my screen.
Yeah. So I think Surat now. Yeah.
I think
he's
you can
hosting.
share. Anyone can share. They have
Okay, you can share it. I think
you can try and see.
Okay, fine. So, can you see the screen?
no, not yet.
Okay, should I stop the screen?
Yeah.
Yeah.
Okay, good. Okay. Now I'm going to go back to.
Now we can only see the Zoom, but yeah, anyway, you can open your presentation.
That's okay. Can you see the?
Yeah. I can see.
Yeah.
Okay, fine. Just. Okay, can you see me writing? Okay.
Yes.
So
Okay,
it's
cool.
white on black. Yeah.
Yeah, white on black. Yeah.
Yeah. Okay. Fine.
Thank you.
Yeah.
So shall I stop the sharing or shall I keep it?
You can just keep it on. I think there is nothing.
Okay.
Yeah.
Okay.
But yeah, we will reconvene in 12,
Sure.
13 minutes. Yeah.
Thank you.
But you can minimize your right hand side.
Yeah, you can
Sorry?
maybe make it a full screen or something because
Yeah. Make it full screen.
Full
Yeah,
screen because
so
right hand side folders are visible.
Visible, yeah.
Yeah. So, but I don't know how to do it. So it's just
In fact, your Zoom yourself are visible in this.
you cannot see my Zoom.
No, I'm saying that
We can see.
we can see your full screen, which includes the Zoom participant list.
Oh, okay.
So,
just minimize it. Just I think
yeah, you should just press that
okay, good.
white small line. Yeah.
Yeah. This is all good, no? Yeah. Okay.
Even now we can see it.
Even now you can see it. Okay. I don't know what. Okay, now it is visible. Now it is good.
It's visible, though it's not. I mean,
no, the same situation.
just your desktop screen is visible. I mean, all the files, including the Zoom participant.
Oh, that's okay. I'll just including Zoom participant.
Yeah.
Yes.
Okay, that's very strange. Okay, I don't know how to do this, but I believe that you can see the screen, right? Properly?
Yeah, we can see the screen. Yeah.
Okay, maybe I'll just write and okay. I don't know. Your screen sharing, stop sharing. Okay, this one I don't know how to do.
Sir, I'll stop the screen share and share again, sir.
Yeah.
Yeah, we can try again. I mean, 5 minutes before your talk, we can try.
Yeah, sure. Okay. Thank you.
Yeah.
Jacquet, you there?
You can see me, no?
Hi, Anil here. I know, I was just saying hi.
Hi. Oh, Anil, how are you? Good to see you.
I'm good. Good to see you too.
Yeah.
How are you?
Good. Nice talk. Great talk.
Nice.
Yeah, is your paper with Bhaskar.
Okay. Yeah. We have been working on for a long time, and then once in a while get some result and then say something.
Yeah. Good.
So maybe Devarga, can you try to share your screen? Just sorry.
Okay.
Set up.
Can you see the thing? Screen?
No.
No,
not yet.
Okay. Sure.
Yeah, it's coming now. Yeah, we can see the screen. Yeah.
No, but I do not see the screen. Yeah. Now you can see the screen?
Yeah.
Quadratic twist.
You can see the screen. Yeah.
I'm writing that. You can see I'm writing, right?
No. We see the desktop screen only. So background.
Background. So that is okay. I'll just stop sharing again. Okay. Share screen. Okay. Sure. Can you see quadratic twist? No?
Yes. Now it's visible.
Yeah.
And I'm writing something.
Yeah,
can you see?
we can see the.
Okay.
See what you're writing.
These always give me means like BP. My BP goes high with this.
No, it's fine. Yeah.
Okay, good.
It seems there is a question for Anil.
Yeah, Anil, can you see Anil?
Okay.
Yes, I do. Yeah, that is true. Yeah, but they're optimal in K. Yes, they're optimal in K, of course.
So Devarga, you're in ISA Pune?
Yes, I'm in ISA Pune. I'm here for some time now, 8 years.
How is Bhaskar?
Yeah, he's doing good. I meet him every day. Yeah, he's good. Yeah, he's around. Yeah, now in pandemic, people cannot go out. Yeah.
Yeah, so say hi to him. I haven't recently talked to him. So.
Yeah, I will tell. Today evening I'll meet him. He goes for a walk every day. I meet him.
Okay.
So the SRM University is in Hyderabad, or it's where is this situated?
This is in Amaravati, so near Vijayawada.
How far it is from Hyderabad?
Maybe
300 kilometers.
300 kilometers, yeah.
Oh, that's very far. Okay.
6 hours drive or less. Roads are very good.
Yeah, sure. I think Ganesh's house is near that, right? Rajmundi. He's from Rajmundi.
I think it's from Vijayanagar. It's not.
Vijayanagar. Yeah.
It's a bit away. It's
a bit away.
Kilometers. Yeah.
Oh.
This Andhra Pradesh new capital.
But there is a dispute, right? I mean, new seems. Is it new capital?
One of the 3 new capitals.
3
Okay.
Legislative.
Okay.
Okay, so we have another 30 seconds. We can start. So the title you wrote is different from the title in the.
Yeah, a little bit different. Epsilon different. Okay.
So can we start, Sajjad?
Yeah, please.
Yeah.
Okay.
Okay, so welcome back everyone for the second talk this morning. We have Devarga Banerjee. He will talk about quadratic twists of local epsilon factors of modular forms. Go ahead.
Okay, thank you, Krishna, for introduction, and thank you very much, the organizer, for giving me an opportunity to speak in this wonderful conference. So today I'm going to talk about with my the work joint with my student. So I'll go very slowly. Please ask me questions if you have. Okay, so I'm starting point is that F belongs to Sk and psi be a new form. So this kind of modular forms, it is already there in Anil's talk, and I think it was there before also. It's a modular forms of weight k and level n and Neyman type of psi. Now the psi is going to give you a character from Z mod nz star to C star. So this is a Neyman type of character, and we ask that it is a new form. It's a Hecke eigen form. It appeared in the Anil's talk also. So it has a basis. If you start with the model of cusp forms of weight k and level n, then it is going to have a basis consisting of a new form, and I'm starting with that. Okay, I don't know how to go. I don't know how to go down. Next, okay. So let's take this I, and so you have this Fourier expansion f like summation over n equals to 1 an q power n. This is a Fourier expansion of this modular forms, and then q is e to the power twice pi I z. But what is amazing is that you adjoin all the Fourier coefficient of the modular forms. It is going to give you a number field, and this is an important number field. This is a number field q. Okay, so this is a number field. So now what I'm going to do is that I fix a prime p. Fix. And this is absolutely arbitrary. I will take anything. And now this natural number, this is the level of the modular forms. I can always write is as n to the power, sorry. Okay, so this p is p any prime. I can write this n as e to the power np times n prime. And I can write this character. I started with the modular forms is a character. I can write with the power psi p and psi prime. Psi p is the p part of that conductor, and psi prime is a prime to p conductor. So this I write this conductor of psi p as p to the power cp. So well, it's pretty obvious because psi is a character on Z mod nz star, and then psi is a character, and this psi p is the this psi is a conductor of psi p is p to the power cp. So what you have is np is greater. Yeah.
What is n here? N equal to n p power np times n.
Times n prime.
Okay, n prime.
This prime to n prime. Yeah. Okay. This is okay. This is away from p. Okay. Okay, so NP is greater or equals to CP always. This is true. Okay, and this is very important when we can talk about this automorphic representation. Okay, so NP greater or equals to CP. Now what I'm going to do is that you can associate to modular forms if this is what Anil was calling a Jacquet-Langlands. It's from an automorphic representation. You get a representation on a certain quaternionic Shimura curve. But I'm talking about a simple first Jacquet-Langlands. So you start with the modular forms. We can associate to a automorphic representation pi f. So this is an automorphic representation from GL2 of A, this Adel groups of A to this bounded operator on a certain infinite dimensional Hilbert space. Okay. So this A is the Adel groups of Q. Groups of Q. Of Q. And H is certain infinite dimensional Hilbert space. Hilbert space over this field E. I am starting with this phi E. E is the field obtained by adjoining all the Fourier coefficients. So this Hilbert space is over this E. So this E is very important. E is this Q adjoint AN. Okay. Okay. Now, okay. So now I'll just talk about now this this pi FP. So this is going to give you this pi. This is pi F. Now breaks down into several restricted tensor product of pi FP. Okay. Now this each of this pi FP is going to give you a representation from GL2 of QP to bounded operators on Hilbert space, but now over E lambda. Lambda is a place lying over P. Okay, so I need to be really careful here. Lambda not equals to P. So lambda is the place lying over L maybe, and L is a prime different from P. Okay, so now what? So why I care about this kind of project? So then this pi FP, there is a few possibilities. Okay, this pi FP is this is the local representation, and this has a few possibilities. So this is unramified principal series. So this is induced from a Borel subgroup. So this case will occur if this P does not divide N. So you're starting with the modular forms and you have a certain level there. If you have P does not divide N, this is going to be unramified principal series. And this is Steinberg. If NP equals to 1 and CP equals to 0. Okay. And then you have this ramified principal series. Principal series. Principal series. If NP equals to CP. And the last case, it is the most exciting case, and this is supercuspidal. Sorry, I just write it here. Supercuspidal. This will occur if NP greater than CP. Okay, so the project which I am trying to understand is what is this pi FP if you have a supercuspidal representation. I will explain to you what is what I am trying to achieve with that. And this information about this pi FP is encoded in the local epsilon factor. So I will define that. Okay, now I will just go back a little bit slowly to how does this pi FP looks like, because I didn't define it because it's a pretty, but it's there in the Bumps book on automorphic representation. Okay, so I just is a motivation of this kind of work. So now we have a character psi. Let me remind you, psi is a character from Z mod NZ star to C star. Now I can write it as this pi psi. So I can see it as a character. This is on this Z mod ZP star. This is Z mod NZ star. This is equals to product over P Z mod P power N Z star to S1. This is all, these are unitary characters, and this is going to give you this product of this. So this is going to give you this local representation. So this analog pi FP that I defined for a modular forms, this is analog of this pi P's. Okay, and why we care about it? Because it's a influential thesis. He proved that this lambda SI, this is defined to be, you have to take this infinite factors, infinity of SI, it has a functional equation, and this breaks up into product over P. This is, you have to take finite, infinite both places. Is pi P, and it satisfies functional equations. Sorry. Functional equation equation lambda SI equals to this epsilon of SI lambda of 1 minus SI. So this is the epsilon factor, what we are trying to understand for modular forms. Okay, so this is for a character. So this is John Tate did in his this is long back. So what we are interested in, this epsilon factor, it breaks up into product over local epsilon factors. Okay, and what is true is that this remark, I would like to take a remark. This epsilon p depends on a choice of an additive character. However, the global epsilon factors does not depend on the choice. Okay. Factors is independent of choice. Okay, now I'm going to define okay, what is this project I'm doing here. So as I told you, you can associate to it F, an automorphic representation pi F, and this pi F also satisfies this L. You can talk about this L function associated to F. Associated to F, and this you can talk about this completed L function. So it breaks up into this infinite factor pi F and Ls pi F, and the same this functional equation, same kind of functional equation holds, which is of the form epsilon pi F by lambda 1 minus this pi F. And the same thing holds, is epsilon pi F breaks up into this product over P is finite epsilon P. And there is, I am just hiding something under the carpet, there is a additive character involved. And the project that I am just embarking on is the following. Okay, so this project is the following. So that is why there is a change in title. I wrote this this variations, but it is this. So VP is epsilon pi FP. This is pi FP is a local representation, not a global. Okay. Tensor of chi p. This is choice of this phi p is an additive character. Pi epsilon pi FP, phi p. Okay, so this is this variation I want to understand. So this is a project, and phi p is additive character, and chi p is a very suitably choice. So chi is a character, quadratic character. Chi character is a quadratic character. Sorry. Ramified only at P. Now the first, so you're going to ask me that why you care about it, but before that, is that any questions? I will review. This is a project I will try to understand in this thing. So this valuation I want to understand. Okay, any questions? I will tell you what is the motivation for that. Okay. Okay, so no questions. Okay, so
by the quadratic character I've heard only at P, you mean that your base field is QP?
So no, yeah. So chi is a character on over Q. So it's I want to see is that a additive character. So it is just it takes values plus minus 1,
okay.
and it's ramified only at P. Okay, suitably. Okay, yeah. Okay. So what is the motivation for looking at this kind of project? So I just want to tell you there is a one global epsilon factor and this is local epsilon factor. but I'm looking at prime by prime, and I'm looking at the local epsilon factor. And there is a phi p. There is a choice of an additive character phi p. I did not.
Someone raised hand, I think.
Yeah. Sorry, I cannot see the screen. Okay.
Can
Someone
you
can you? Yeah.
Can you unmute yourself and ask?
Okay, maybe I will just answer after after the talk. So this is the project, okay, and it is very.
Speak now. I don't know whether
Hello?
he's able to speak.
Yeah.
Go ahead.
I can see.
Yeah, so I have one question.
Yes.
So what is the reason to consider only a quadratic character?
Because that is sufficient to answer the questions. There is some certain applications. So that is sufficient to answer that questions. Okay, so I will come back to. So as I told you, I started with this pi fp. So I'm interested in this all the other cases, ramified, unramified cases, and more or less, I mean, before me it was being understood. But the supercuspidal, so this is difficult, and I want to have certain arithmetic information coming from pi fp. So that information I want to have. So VP, if you can calculate, so you can calculate anything. Okay, so you can take it for chi, quadratic, cubic, anything, but it should give some arithmetic information. So that VP, if you do this, calculate this quantity, it is going to give you certain arithmetic information. Okay.
I see. Okay. Thank you.
Yeah, welcome. Okay, so I'll just tell you. This is related to this question. So you have this theorem. This is a very well-known theorem. Of course, any mathematics in our time, this is it will not be done without this mention of this theorem. So this is goes back to Shimura for weight 2 maybe, and this is for Deligne and for higher weights. So you can associate this. You start with this E over Q. This E is a number field, as I told you. So you start with the modular forms. I have to start with the modular forms of certain weight, certain level, and certain event types. I already talked about this. There exists a Galois representation. Galois representation. Rho f lambda from GQ to GL2 lambda. There is a Galois representation. This is a global representation, and this is associated to an automorphic representation pi f we are starting with, and it has a property that trace. This is a group homomorphism. Okay, so GQ is an algebraic group. GQ is a Galois group, and you have a continuous representation, and this has a property that trace. If you associate to a trace, if lambda of p, you'll get back this AP that we started with. So this E is, of course, this Q adjoined in. Okay, and determinant of this representation -1. Okay, so this is the Galois representation. So what we have, okay, so I am not, I have very less time, so I will not talk about the other cases, means like, okay, so maybe I'll just talk a bit about this. So there is rho f, okay. So this rho f lambda, this is map from GP, each for every P, this is a map from GP to GL2 of E lambda. Okay, and this is Galois group of QP bar over QP. Okay. Now, as I told you, pi fp, you have a certain classification, ramified principal series, unramified principal series, but the main exciting part is if NP is greater than CP. Okay, so I'll just case 4. So this is NP is strictly greater than CP, and NP is greater equals to 2. Okay. This is already, I just talked about case 4 because 1, 2, 3, I just skipping it for this talk. So in that case, is pi fp is supercuspidal. Okay. And the arithmetic question that I want to understand is what can you say about rho f lambda if pi f p is supercuspidal? So this pi f p correspond to this local, there is a p involved. Okay, I'm just hiding it, but this is a restriction. Rho f lambda, you have this Galois representation, global representation. You restrict to this GP, then you get a Galois representation. So what can you say about this rho f p? Well, there is two possibilities for modular forms. There is two possibilities. Case one. So this rho f p is irreducible, and there is inside this GP there is an inertia group, but inertia acts reducibly. Okay. So in that case, okay, I'll remind you. So if you take P to be odd prime, you are always in this case. Rho f p is going to be irreducible, but the inertia will act reducibly. So in that case, this rho f p, rho f lambda, restricted to GP, will be induced from a character GP to GK to theta. Now this theta is a character from GK to E star. And the question, why you care about this quadratic character? The question I want to understand, what can you say about this question? What is K? This K is a number, K is a quadratic extension of QP. Yes, this quadratic extension. What can you say about K? Say about K. I will come in the second question also. That is also you have an answer. But this maybe I'll just go back to the previous thing. So you have this variation. This is the project, and this is going to tell you what is this K, and that's why we care to compute this VP. I will tell you one more motivation, but this is one of the motivation. So this is this VP, and this will help us to determine in the case what is this K. Okay. I will do this case 2. There is this case 2. This is for P odd. It is always the case. P greater or equals to 3. We always has this GP acts this way. Okay. But this case 2, it can happen. It can happen in case 2. This is this rho f p. This is irreducible. Plus inertia also acts irreducible. Well, in this case, there is a few possibilities. This projective image of this well-defined representation. So this is really hopeless. If you work with modular forms, you will see that this is most troublesome of the case. But the projective image of this well-defined representation, you have to go to the projective image, well-defined representation. There is few possibilities. The projective groups are easier to understand. So in that case, there is a few possibilities: A4, S4, and A5. And fortunately, it is already being classical. These two cases will not occur, and this case will occur. And this variation I just talked about, this ratio of this epsilon factor, it is going to tell you when this S4 case happens. So this is one of the motivation. This is motivation 1. This is motivation 1. This is one of the motivation computing this variation. And the second motivation is the following. Question 2. When can you detect when F is P minimal? So I will define for you what is P minimal, but for the experts, so this P minimal means if you twist modular forms by a character, then it is going to give you certain modular forms, but the level is going to increase. Okay, and the P minimal factor, it should be minimum. Okay, I will explain to this. Okay, so this is like an English word, P minimal. So P among the twist, it should have the minimum level. So that is the definition of P minimal. And this VP that I defined is going to help us to determine when this modular form is going to be P minimal. Okay, I will define for you what is this P minimal. So recall this F belongs to SK of n psi, and let's take this chi. This is a character from Z mod MZ star to C star. Then I can talk about this F tensor chi. F tensor chi, and it belongs to SK square psi chi square. And the definition is following. F is P minimal. Sorry. If P power that appears in the level is minimum. Okay, so it is time to give some credit. So this kind of questions we just finished it. The question is being started by David Loeffler and Jared Weinstein. They only define this minimality, and Jared Weinstein, and they wrote a paper around 2013. Okay, maybe it is a plus minus 1-2 years. And this Ariel Passetti, they worked on approximately the same time, 2014. So they started working on this kind of questions, but their answer was not complete, and our project just completed the questions. Okay, so any questions? So this is a motivation for computing this valuation and this variation, and this is that's it. So now I just define this epsilon factor, and I will tell you what are the results. What is our result? Okay. Okay, so I just defined for I defined this. Maybe I roughly spoke about what is the global epsilon factor. But I didn't talk about this local epsilon factors. So you have this AF over QP. So you have this ZP. And then you have this OF. Okay. And then you have this UF inside this. This is 1 plus PZP. Okay. So you have a filtration. So definition, you fix a character. Okay. So I'm doing everything. So this is, you can talk about for other groups also, but I'm interested in modular forms. So I'm defining everything more or less in the context of the modular forms. Okay. So star at phi is a map from. This is an additive character. So epsilon phi c is q to the power minus phi 2. Sum over x belongs to phi chi inverse of x phi of. Okay, so then this is q. Okay, q is a residue field. Okay, so there is a dispute in this area about what is the conductor, and more or less for this project, I just take it Bushnell-Laniert as a building block. So our definition of the conductor coincides with the this Bushnell-Laniert's definition. Okay, so I will now talk about what is the first time here. This is motivation for this. This is a theorem. This main ingredient, I will take you first. What are the main ingredient? So it goes back to a theorem due to Delin, approximately 1973. which says that, let's take this alpha, beta, two characters. Of F star. Okay, and such that A alpha beta equals to twice A beta. Okay, so if alpha of 1 plus x equals to phi f of cx. So under certain condition, for all x belongs to pf to the power r with twice r beta equals to a alpha. And this is strictly greater than 1. This is very important. I was just put, maybe I do have read. Okay. Okay, good. This rate is working. Good. Okay, so this is strictly greater than 1. So then n of alpha beta by f comma c, this is equals to beta inverse c epsilon of alpha by f comma c. Okay, so this is our starting point. Okay, so any classical things is being a starting point. I will just tell you what are the ingredient it is needed to this. By the way, I didn't define this A alpha. A alpha is a conductor of this character chi alpha. So I am not hiding. I'm hiding what is the definition. But this is the smallest m for which is in the filtration. This is the smallest m for which is in the filtration. This is the smallest m for which it is trivial and there is ambiguity, but I will follow this Bushnell-Henriet's definition. Okay, so what we realize is that we need to get, okay, there is a in this area of mathematics, there is a way for going from translating from a multiplicative character to additive character. And the following lemma, so this is our first lemma, this is lemma proved. And this is inspired by this work of Takeshi Saito. Inspired by Takeshi Saito. So our work is motivated. I mean, you can ask me what is the difference between the opacity and all these works. But this is the we use this Takeshi Saito's work. Okay, and this inspired by Takeshi Saito. If you take this chi belongs to this F star hat, so that means the character, and phi f belongs to F hat. So let r belongs to a natural number such that twice r is greater or equals to a chi. So that implies there exists C belongs to F with valuation minus a chi plus n phi. So this is all this conductor additive characters and multiplicative characters. Okay, such that okay, phi of 1 plus x equals to phi f cx for all x belongs to pf to the power. Okay, so I'll just give you some few lines of how this I can prove this. So this is again, this kind of conditions are very important, and I will tell you why we will get into trouble if you do not have this condition. Okay, so do this. So we have this twice r greater or equals to a chi. Okay. Okay, so then what you have, this chi of 1 plus x, this condition is going to tell you that chi of 1 plus x to chi of 1 plus y equals to chi of 1 plus x plus y. So that is going to tell you that x goes to chi of 1 plus x. This is an additive character. Now again, I go back to Bushnell-Henriet. Okay, so in this project, we use this Bushnell-Henriet very, there's heavy use of this book. It's a very good book, and it's a GTM books, Henriette. So it's in the first chapter only. So this phi f c, so C belongs to F. This is that F hat. Okay. So this chi of 1 plus x coincide with one of these characters. Okay. So that implies this chi of 1 plus x equals to phi f of cx for all x belongs to P. And this is going to tell you this n of phi f c equals to minus n of phi f plus P of c. As I told you, I always use this Takeshi-Saito's and even Deline's. This has a condition, and this condition is we cannot. So we cannot remove this condition. So what you have to do is that if you get into trouble there, so you have to use something else, and that is this Morita's periodic zeta gamma functions. So in this case, a chi equals to 1. One function. So in that case, this gamma pz, this is defined to be gamma pz equals to limit n tends to z minus 1 to the power z over 0 less than g less than n. Okay, so now I'm just talk about this our theorem. Okay, so this theorem due to self and I'll tell you how does this variations looks like. So if you have this k over qp, so I will talk about only in case 4. Huh? Case 1, 2, 3 also I computed, but it is not very different from the previous walk. So I'm not explaining. It is there in the paper, so you can have a look. So if k over qp is unramified principal series, unramified supercuspidal. So as I told you, so in this pi fp, it is going to give you supercuspidal representation, the corresponding Galois representation. It is induced from a character. There is two possibilities. Either it is unramified k or a ramified k. So if you have an unramified, this corresponding supercuspidal representation, we call it unramified supercuspidal. So in that case, this Vp equals to 1 if a chi is greater or equals to 1. Okay. Okay, so okay, sorry, in this is really I need to be really careful. If I is strictly greater than 1. 1. 2, if a chi equals to 1, A is M even. You have this Vp equals to 1, and there is B M odd M and M divide. So this result is for general, right? So in that case, this Vp is determined by this Morita's periodic zeta function. This is gamma p 1 by m p by twice m square. And C, if m divides p minus 1, then implies Vp is minus 1. Okay, so I can talk about this. Okay, I have 1 minute. So if k over q is ramified, okay, so 2 k over q is ramified. Okay. And p odd in that case is a theta odd implies Vp equals to 1. And 2, if a theta is even, that implies F is P minimal. So in that case, if A theta is even, then F is P minimal. And in that case, I can compute this VP as 1 if K equals to QP square root of minus P. So as I told you, the Y you should there Y you can help us to determine this pi of P because it is C of variation. That's 1 by P if K equals to QP minus P zeta P minus 1. Okay, and this is complete classification for this K odd. So P if P is odd, then this is what, and if P is equal to 2, so interesting thing happen. So any questions? Just wait for this. These are the two results for P odd. As you know, for most of the time it is going to be odd, and this is what happens, and I'll tell you what is the result for P equals to 2. And you can see this is the reason why you can detect what are the field it will happen, because it will precisely tell you. So what are the, if this is 1, then okay, you compute this. Okay, so you are going to tell that why you can you start with the pi fp. We don't know if it is coming from with this K or this K. These are two different Ks. So but then these epsilon factors we can compute. Okay, so if you can say, okay, so this epsilon factor is minus 1 by P, then you can say, okay, K is like this. Okay, so that determines pi fp completely. Okay, and now you are going to ask me why you care about this. This is going to helpful this pi fp. This is other arithmetic information because this pi fp has other informations. Okay, I will tell you about what happened if P equals to 2. So okay, so P is equal to 2. Oh, it's already this, no, P equals to 2. And then this is V2 equals to 1 if K equals to U2 square root of 2 T, and T equals to minus 1 to minus 2 minus 6, and minus 1 if K equals to Q2 square root of 6, and theta minimal. So this kind of information is also there in this with these variations. And 1 if K equals to Q2 to 6, and theta non-minimal. Okay, so this is the result for P equals to 2. And now I'll just give a briefly sketch what is the proof of this theorem. Okay. Okay, so let's give a proof. So let me recall for you. So if you induce, so as I told you, so I'm interested in this epsilon factor and epsilon factors, and in this case, what we know, it is there in the time of Delin and all, and this is the Langlands classification that pi f p, this corresponding rho f lambda, is induced from a character. So in this case, you have this is this is well group, huh? This is the image of Z inside this Z hat. So this is WQP to WK of theta. You twist it by the character chi p. Okay. So now this is induced from WQP to WK of theta chi p squared. Okay. So now let me recall for you this chi p prime. I talked about this chi p prime. This is chi p opposite norm of P over QP. Okay. Now what you have? What you have is the following: norm K over QP. So let me recall for you, this K is a quadratic extension. Okay. So this is over OK star. This is algebraic number theory. So this is going to tell you Z P star. Okay, so now what I'm going to do is that following. So epsilon theta phi prime phi k, and there's a R measure involved. This is equals to phi p norm q over qp. So these are all local things, huh? So x to the power ak plus 1 times epsilon theta phi k. Now this is, what is this Vp? Vp is nothing but chi p of norm k over qp of this pi. Pi is a uniformizer of k. So this is norm by p. Okay, so so now what you have is norm k over qp. So depending on this, what case you are in, ramified or unramified. So this pi equals to minus pi square. Okay, so then this is Vp equals to minus pi square by p by p. Okay, so this is okay. This is not a proof. There is some involved here. So please check the paper for this in between computation. So Vp equals to 1 if p over qp equals to 1. It just means that the norm sits inside qp or not, and this is minus 1 by p if p over qp equals to minus 1. And let me recall for you some properties of the epsilon factor. Properties of epsilon factor. So well, for this this is all goes back to Delin, huh? This is epsilon factor. One is the following. So, theta phi equals to theta pi f to the power a chi plus n phi epsilon induced wqp to wf wk of rho phi is equals to epsilon rho closed trace of f over q of phi. So I'm just hiding this. What are the other factors involved? Okay, so using this, we can tell. So this is epsilon factor. If you do that, so then we have. So at the end, I will just tell you what is the classification of k. So classification of k is the following. So this is very beautiful as a if you compute these VPs of k. I assume that f is a new form. Huh? So everything is a. Let me recall. This is the first hypothesis in the first slide. P is odd. NP is greater or equals to 2. That implies Q over QP is unramified. Unramified. And NP is greater or equals to 3. Odd. And P is congruent to 3 mod 4. So then, okay, 1. K equals to QP to the power QP of square root of minus P. Minus P. If you can check this is easy to check. This is a global epsilon factor condition. Epsilon F tensor chi P equals to epsilon P of F chi P of n prime. N prime is this prime to n part in the first slide, and 2 k equals to 2p square root of minus p zeta p if epsilon of f tensor phi b epsilon f, this is difference. This is here. Okay, I'll just read it because there is epsilon p here, phi p of n prime. Already okay. Okay. So this is the classification of k. So for p equals to 2, I will not talk about because I already am wasting time. Okay, I will stop here. So this is how it is. This is the usefulness of this computing this variation. I will stop now and please ask questions.
Thank you, Debarga. Are there any questions?
Yeah. Yeah, I have a couple of questions.
Yeah,
Yes,
go ahead.
please.
Yeah. So if lambda equal to p, so then what will be the situation? The lambda you chose.
What do you mean by that? Okay, lambda
So
can be
lambda
p.
means
So,
that
so there is a
local-
lambda. You are talking about, just a minute. I'll go to this. Which lambda you're talking about?
Yeah, that means you the local representation, 2-dimensional. That is
No, that is not. This is always, this is supercuspal. It will not be QP. So you're talking about supercuspal case, right?
Yeah.
So supercuspal case, it will not be because it is induced from a character. So this information is already given. It is induced from a character. So it's a quadratic extension.
Okay. So one more question is that, okay.
Yeah. Okay.
So regarding the classification of K, that quadratic character you have chosen, that is not determined via classical theory. That
yes, that is determined. Yeah. That
there is the use of VP. So VP is just
VP. Okay. So okay. So yes, VP is in between, but now. So this is a theorem also. It's a part of our work as a consequence of our work. So you can say if you can, this global epsilon factors are computing. If you look at modular forms, you can compute the global epsilon factor. Okay, and this epsilon p and chi n prime, you check this. If this condition is satisfied, then you can say k equals to qp square root of minus p. And the other condition is satisfied, then you can say k equals to qp of. So okay, so a priori what information we have from Langlands is that k is a quadratic extension. Okay, but what extension k will that is Langlands will not tell you. Okay, so what we for arithmetic information we need to name which of these the two quadratic field will occur. Okay. So our consequence of our theorem. So this theorem is the following. It will tell you, okay, you check this equality. This is an equality. I mean, you can Sage also can compute this equality satisfied or not. Okay, you can, this is satisfied is at this prime p, k is like this, and the other case k is like this. So this is a dichotomy that you can this is a theorem. Classification of k is a theorem, our theorem, and this is the consequence of this VP. Did I answer your question?
Yes.
Yeah.
Thank you.
Yeah. Okay.
Are there any other questions? Okay, so if not, let's thank Debarga for a very nice talk. Thank you.
Thank you very much.
Okay, so the morning session is now over. We'll reconvene at 2 o'clock. Bye.
Shayan Ghosh has a question.
Oh, I see. Right, yes.
I think he left, I think.
No, Debarga is present.
Yeah.
Debarga is here, yeah. So I think if Sayan can ask.
Yeah. No, but I don't think there's, I have a question that is, that then, I do not see the question. Can you see the question and ask?
No, it could be that he's about to write. Maybe, I don't know.
Or he can just ask.
Yeah, he can just unmute and ask.
Yeah.
Sayan, could you ask the question? I think somebody should
Unmute.
Yeah.
Yeah, I can see one more people raised hand.
But they have
Yes.
Yeah.
Did I resent? Okay, by mistake. I don't know this.
Ayan, are you there? I don't know.
Yeah, he's there.
But I think because of our this setting, he is not able to ask question.
New
It is
message.
network issues.
Oh, he's writing. He's writing. yeah.
Okay. Mhm.
Yeah, let me post the picture. We uploaded channel like YouTube.
Okay.
Okay,
I think it
that's
will
not
be uploaded.
mathematical.
Yeah,
It's
uploaded
not a
on
mathematical.
YouTube.
Okay, I can send you this.
YouTube, it's already
PDF of
there.
this.
So
Yeah, it's
Yeah,
already
yeah,
there. Yeah, sure.
Should be
Yeah.
available.
So in YouTube, this whole conference, I think it's live telecast thing. So
Yeah.
I think later on also you can check. It will be.
Hmm.
and if you can write to Debarga, we can.
Yeah, I can.
So link will be given on this website, conference website.
Yeah.
Okay.
Thank you, Devargada.
Thank you. Thank you very much.
Thank you.
Thank
Yeah.
you. Thank
Bye.
you. Bye.
Now you can